There's a place in the cosmos where the laws of physics seem to bend, where newborn stars flicker like candles in the wind, and where mysteries hide in every swirl of dust and gas. Welcome to the Orion Nebula, a jaw-dropping stellar nursery just 1,500 light-years away, and one of the most active, chaotic, and breathtaking regions in our night sky. This isn't just another cloud of space debris. It's a cosmic cradle where stars are born, where planets take their first breaths, and where phenomena so strange they defy explanation unfold right before our eyes. Imagine staring into a kaleidoscope of celestial fire, where colors shift from deep crimson to electric blue, where pillars of gas stretch taller than our entire solar system, and where invisible forces sculpt the landscape like unseen hands molding clay. The Orion Nebula isn't just beautiful, it's alive with activity, a place where the universe itself seems to be experimenting, creating, and occasionally breaking its own rules. And tucked within its glowing heart, 30 of the most bizarre, mind-bending oddities astronomers have ever witnessed. From stars that vanish without a trace to rogue planets hurtling through space at unimaginable speeds, this nebula holds secrets that challenge everything we think we know about how the cosmos works. But why does this matter to you? Because the Orion Nebula isn't just some distant spectacle, it's a window into our own origins. The same violent, beautiful processes happening there once shaped our sun, our Earth, even the atoms in your body. Every time we peer into its depths, we're glimpsing the past and the future of star birth, of planetary systems, and perhaps even of life itself. So buckle up, because over the next few minutes, we're diving deep into 30 of the most astonishing, head-scratching, and downright eerie phenomena hidden within this cosmic wonderland. By the time we're done, you'll never look at the night sky the same way again. Right in the heart of the Orion Nebula, a peculiar structure slices through the glowing gas like a cosmic knife edge, an enormous glowing barrier known as the Orion Bar. This isn't just another wispy cloud of interstellar material. It's a dense, almost solid-looking wall of gas and dust that stands out starkly against the nebula's vibrant backdrop. What makes it so bizarre? Unlike the delicate, wispy tendrils seen in most nebulae, the Orion Bar is remarkably sharp-edged, almost as if it's been sculpted by some unseen cosmic force. Scientists believe this glowing barrier acts like a shield, absorbing the intense ultraviolet radiation pouring out from the nearby Trapezium stars, a cluster of hot, young stars that flood the nebula with energy. But here's the mystery: the bar shouldn't exist in its current state. Based on our understanding of how gas and dust behave under extreme stellar winds, this structure should have been torn apart long ago, scattered into the void like smoke in a hurricane. Yet there it stands, unyielding, defiant, almost as if nature itself is refusing to follow the rules. The Orion Bar isn't just a cosmic oddity, it's a laboratory for star formation. Deep within its dense layers, molecules like hydrogen and carbon monoxide huddle together, shielded from the deadly radiation outside. In these shadowy pockets, the raw ingredients for new stars and even planets can safely cling together undisturbed. That makes this bizarre structure not just a scientific puzzle, but a cosmic cradle in its own right, one that might be silently nurturing the next generation of stellar systems. But the mystery only deepens when astronomers try to pinpoint why the bar is so resilient. Some theories suggest magnetic fields threading through the gas might be reinforcing it, like invisible scaffolding holding up a collapsing building. Others propose that turbulent shockwaves from nearby stellar explosions could be compressing the material, making it far more durable than expected. The truth: we still don't know. Every time we think we've cracked the Orion Bar's secrets, it throws another curveball, reminding us that even in the most studied corners of space, the universe still has a few tricks up its sleeve. At the blazing core of the Orion Nebula, 4 brilliant stars dominate the scene like celestial monarchs: the Trapezium Cluster, These aren't just any stars, they're massive, volatile infants, barely 1 million years old, burning so ferociously they flood the entire nebula with enough ultraviolet radiation to rip atoms apart. Picture standing next to a hurricane while it's being born. That's the kind of raw, chaotic energy these stellar powerhouses unleash every second. What makes the Trapezium Cluster truly extraordinary isn't just its blinding glow, but the way it sculpts the nebula itself. Like cosmic artists, these stars carve vast cavities in the surrounding gas with their stellar winds, pushing and twisting the nebula's structure into those iconic, billowing shapes we see. But here's where things get strange. Scattered around these titanic stars are hundreds of smaller, fledgling suns, each one swaddled in a swirling disk of gas and dust called a proplyd. These disks are the birthplaces of future planetary systems, cosmic nurseries where worlds could one day form. Yet in the trapezium's brutal glare, these proplyds aren't just growing, they're fighting for survival. The cluster's radiation acts like a celestial blowtorch, evaporating the outer layers of these disks at staggering speeds. Some proplyds are being stripped so fast they resemble comets, with vast tails of vaporized material streaming behind them like cosmic kite tails. It's a race against time. Will these disks coalesce into planets before the trapezium's fury tears them apart? Even more bizarre are the proplyds that seem to defy the odds. A handful of these disks appear shielded, as if wearing invisible armor against the radiation. Some might be protected by dense cocoons of gas, while others could owe their survival to sheer luck positioned just far enough from the cluster's wrath to cling to their material. These resilient disks might hold the key to understanding how planetary systems, like our own, can emerge from such violent environments. The Trapezium Cluster doesn't just shape the Orion Nebula, it's rewriting the rules of star and planet formation. Every observation peels back another layer of mystery, revealing how even in the most hostile corners of the universe, the ingredients for new worlds persist against all odds. Hidden among the glowing tapestry of the Orion Nebula, one star behaves like no other. A celestial enigma astronomers call the Great Orion Nebula Variable. This isn't your typical twinkling point of light. It's a cosmic rebel flaring and fading at random, defying every expectation of how young stars should act. One month it shines brilliantly, outshining its neighbors. The next it dims to a faint whisper, as if something or someone is flicking a cosmic dimmer switch. The strangest part, this isn't just a case of a star pulsing rhythmically like a heartbeat. The Great Orion Nebula Variable changes its brightness chaotically with no discernible pattern. Some astronomers have compared it to a car engine sputtering unpredictably, sometimes roaring to life, other times stalling out mid-flight. The leading theory suggests this star might be playing hide and seek with us, its light partially blocked by a swirling, messy disk of gas and dust. Imagine trying to peer at a flashlight through a tornado of smoke. The beam would flicker wildly as dense pockets of debris pass in front. That could explain why this star's glow seems so erratic. But there's another, even wilder possibility, an unseen companion. Some researchers speculate this star might be locked in a gravitational dance with another object, perhaps a smaller star or even a massive planet whose orbit periodically eclipses the primary star's light. If true, this would make the system a cosmic hall of mirrors, where one body's movements indirectly betray the presence of another we can't even see directly. The most baffling aspect, though, is the sheer violence of these fluctuations. At times, the star's brightness swings by staggering amounts in mere weeks, a volatility rarely seen in stellar nurseries. One hypothesis points to clumps of material dense, planet-sized globs of gas crashing into the star's surface like celestial meteors, triggering sudden flares. Others wonder if magnetic fields, twisted into knots by the star's rapid rotation, might be snapping like rubber bands, releasing bursts of energy that temporarily amplify its glow. What makes the Great Orion Nebula Variable so compelling isn't just its odd behavior, but what it reveals about the messy, unpredictable nature of star formation. Most newborn stars shine with relative stability, their light steady as they settle into maturity. This one, though, it's a cosmic toddler throwing a tantrum, a reminder that even in the controlled chaos of the Orion Nebula, nature still has surprises up its sleeve. Every flicker, every unexplained dimming is a clue waiting to be deciphered, a piece of the puzzle that could rewrite our understanding of how stars are born. Beyond the dazzling glow of the Orion Nebula lies something far more mysterious, a shadowy empire of gas and dust so vast it dwarfs the nebula itself. This is the Orion Molecular Cloud Complex, a sprawling network of frigid, dark materials stretching hundreds of light-years across space. Here, temperatures plunge to just a few degrees above absolute zero, creating an environment so harsh it would freeze the very air in your lungs in an instant. Yet within this cosmic deep freeze, something extraordinary is happening, the silent, patient birth of stars. Unlike the nebula's fiery chaos, the molecular cloud complex operates in near total darkness. Its dense pockets of hydrogen gas and microscopic dust grains drift so thickly they block all visible light, turning entire regions into black voids against the night sky. But peer deeper with infrared or radio telescopes and you'll uncover a hidden metropolis of activity. These clouds aren't empty, they're factories. Inside their icy depths, atoms link together to form molecules, some as simple as hydrogen gas, others shockingly complex. Astronomers have detected everything from carbon monoxide to formaldehyde, even ethanol, the same alcohol found in your favorite drink, the real stunner. Organic molecules, the kind that form the backbone of life. Compounds like methanol, acetylene, and even amino acid precursors have been spotted swirling in these clouds. It's as if the universe is brewing a primordial soup, tossing in ingredients that, under the right conditions, could one day spark biology. That raises a tantalizing question. Could the seeds of life be hitching rides on comets or asteroids, forged in clouds like these before drifting to planets like Earth? What makes the complex so special isn't just its chemistry, it's how stars emerge from this molecular soup. Gravity slowly tugs gas and dust into dense knots, and as these clumps grow heavier, they collapse under their own weight. The center heats up, atoms smash together, and suddenly ignition. A new star flares to life, often surrounded by a disk where planets might form. But here's the twist. The same organic molecules that float freely in the cloud become part of that star system, embedded in comets, asteroids, or even fledgling worlds. The Orion Molecular Cloud Complex isn't just a star nursery, it's a cosmic pantry stocked with the ingredients for worlds, and possibly life itself. Every molecule drifting through its icy depths whispers a story about how the universe builds not just stars, but the very chemistry that makes living things possible. And that story might hold clues to our own origins, written in the faint radio signals of distant, frozen gas. Deep within the Orion Nebula's luminous embrace, hidden from ordinary telescopes, lies a cosmic battlefield so violent it reshapes the surrounding space, the BNKL infrared source. This isn't just another cluster of stars, it's a chaotic epicenter of collisions, explosions, and raw stellar fury, all playing out in the eerie glow of infrared light. While the nebula's visible regions dazzle with color, this hidden realm only reveals its secrets when observed through the lens of infrared astronomy, where the veil of dust is lifted and the true drama unfolds. At the heart of BNKL, massive stars, some dozens of times heavier than our Sun, wage a gravitational war, hurtling past one another at speeds that defy imagination. The sheer force of these close encounters sends shockwaves rippling through the surrounding gas, heating it to millions of degrees and triggering violent outbursts. What makes this region so extraordinary is the scale of destruction. Astronomers have detected vast outflows of material, some stretching light years into space, like cosmic scars left behind by ancient stellar skirmishes. Infrared observations peel back the layers of this chaos, revealing a spectacle invisible to the naked eye. Here, young stars still wrapped in their dusty cocoons unleash jets of superheated gas, punching through the nebula like celestial blowtorches. Meanwhile, others, perhaps the losers of these gravitational tugs of war, are flung outward at breakneck speeds, destined to wander the galaxy as rogue stars. The most shocking discovery, traces of what might have been a colossal stellar collision, an event so powerful it could have briefly outshone the entire nebula before fading into obscurity. The energy pouring out of BNKL defies expectations. Some theorize that the region acts like a stellar pressure cooker, where the cramped conditions force massive stars into deadly dances, spinning faster and hotter until they erupt or merge. Others suggest the explosive outflows are remnants of a chain reaction, one star's demise triggering its neighbors to collapse or ignite in a domino effect of cosmic violence. Yet for all the theories, BNKL remains an enigma, its full story still shrouded in dust and mystery. What makes this infrared battlefield so crucial to understanding the Orion Nebula isn't just its violence, it's the way it shapes the future. The shockwaves and radiation from BNKL compress nearby gas, carving out new niches where the next generation of stars might form. Even in destruction, this region sows the seeds of creation, proving that in the cosmos, chaos and rebirth are forever intertwined. And as telescopes grow more advanced, who knows what other secrets this hidden furnace might yet reveal? Piercing through the Orion Nebula like cosmic bullets, a series of eerie, finger-like jets stretch outward in perfect formation, the aptly named Orion Fingers. These aren't just wisps of gas, they're supersonic shockwaves blasted into space at speeds exceeding 150,000 miles per hour, each one a smoking gun from a violent stellar birth. Picture a newborn star throwing its first cosmic tantrum, hurling colossal streams of energized materials so forcefully they punch straight through the surrounding nebula, leaving glowing trails in their wake. The source of this celestial artillery, a massive young star hidden deep within the nebula's dusty folds, one so energetic it functions like a cosmic particle accelerator. As the star devours gas from its surrounding disk, it also spits out opposing jets along its poles, a process scientists call bipolar outflow. Normally, these jets are relatively orderly, but in the case of the Orion Fingers, something went spectacularly wrong. Instead of smooth, continuous flows, the star seems to have erupted in sporadic, explosive bursts, firing off dense clumps of gas like a machine gun. Each finger marks the path of one of these projectiles, frozen in time as they plow through the nebula's hydrogen clouds. What makes the fingers so mesmerizing isn't just their speed, but their structure. Infrared and radio telescopes reveal they're not random tendrils, they're nearly parallel, as if the star's eruptions were precision-guided. Some stretch over 2 light years long, their tips glowing brightly where they've rammed into slower-moving gas, creating bow shocks that light up like interstellar headlights. Even stranger, the fingers aren't static. They're still expanding, their leading edges racing outward while their tails slowly dissolve back into the nebula's churning currents. The real mystery lies in what triggered such a violent birth. Most stars form relatively calmly, their outflows steady and symmetrical, but this star, it's as if it underwent a series of convulsions, ejecting material in fits and starts. Some theories suggest a hidden companion star might be to blame, its gravitational tugs destabilizing the disk and causing periodic eruptions. Others propose the star's own magnetic field went haywire, snapping and reconnecting in ways that catapulted gas outward in pulses. The Orion Fingers are more than just a stunning visual, they're a fossil record of stellar turbulence. By studying their shapes and speeds, astronomers can reconstruct the explosive history of this star's infancy, learning how the most massive stars rebel against their own formation. And somewhere in that chaos, there might be clues about how our own sun behaved in its youth. hinting that even the most familiar stars might have wild, explosive pasts we're only beginning to uncover. Amid the swirling chaos of the Orion Nebula, two ghostly wisps of light flicker like celestial fireworks, Herbig-Haro objects 1 and 2, or HH1 and HH2 for short. These aren't stars, nor are they remnants of an ancient explosion. Their cosmic scream marks the aftermath of newborn stars shrieking their existence into the void with jets of superheated plasma. Picture a stellar infant taking its first breath, then coughing up twin beams of gas at nearly 500,000 miles per hour, so powerful they slam into surrounding material, lighting up space like a neon sign announcing, "Here I am." What makes HH1 and HH2 so mesmerizing isn't just their glow, but how they work. As a young star spins to life, it doesn't just pull gas inward, it also flings material outward along its poles, creating high-speed jets. When these jets smash into slower-moving gas clouds, the collision is so violent it heats the material until it glows, creating the luminous shock waves we see. The result, a glowing, flaring structure that looks like a cosmic exclamation point pulsing with energy. But here's where it gets even wilder. These Herbig-Haro objects aren't static. They move fast. Over just a few decades, astronomers have watched HH1 and HH2 shift position, their fiery tendrils stretching farther into the nebula as new material gets blasted outward. It's like watching a time lapse of a star's tantrum, each flare and ripple a snapshot of its turbulent youth. Some of these jets even curve or spiral, hinting at unseen gravitational tugs from nearby stars, or perhaps the star's own wobbly rotation throwing its outbursts off course. The most mind-bending detail, the star responsible for HH1 and HH2 isn't even visible. Hidden behind thick curtains of dust, it remains a mystery, its presence betrayed only by these radiant shock waves. It's as if the universe is playing a game of peekaboo, teasing us with clues but refusing to reveal the full picture. Some theories suggest there might be multiple stars involved, their combined outflows twisting into the intricate patterns we observe. Others speculate magnetic fields, twisted into knots by the star's spin, could be funneling these jets into such precise, narrow beams. Yet for all their violence, Herbig-Haro objects are fleeting. In a cosmic blink, just a few thousand years, the jets will dissipate, the shock waves fading as the star settles into a quieter life. That makes HH1 and HH2 rare glimpses into a star's most chaotic, dramatic phase, a reminder that even in the vastness of space, birth is never a quiet affair. And as we study these glowing announcements, we're not just watching a stellar coming-of-age story, we're peering into the same processes that shaped our own sun and every other star in the night sky. Woven through the Orion Nebula's radiant glow, a shadowy labyrinth stretches like a cosmic spiderweb, the dark lanes. These aren't just empty voids, they're dense, twisting ribbons of dust so thick they blot out the light behind them, carving eerie silhouettes against the nebula's luminous backdrop. Imagine holding a stained glass window up to the sun, only to see black threads crisscrossing its surface. That's the effect these dark lanes create on a scale spanning trillions of miles. What makes these filaments so fascinating isn't just their darkness, but their structure. Unlike the chaotic swirls of gas elsewhere in the nebula, the dark lanes often appear unnervingly organized, with some stretching in near-perfect lines or delicate arcs. Some resemble the veins of a celestial leaf, branching and dividing with startling precision. Others twist into braids or corkscrews as if sculpted by invisible hands. The secret: these lanes are packed with microscopic dust grains, tiny flecks of carbon and silicate, each one 1,000,000 times smaller than a grain of sand. But together, they form an impenetrable curtain, absorbing and scattering starlight like a cosmic fog. Peering into these shadowy corridors reveals something unexpected. They're not static. The dark lanes are battlegrounds where gravity and radiation wage an endless tug of war. The Trapezium Cluster's fierce ultraviolet light pushes against the dust, trying to blast it apart, while gravity tugs the material inward, compressing it into even denser knots. This struggle creates bizarre, dynamic shapes, some lanes fraying at the edges like worn rope, others collapsing into dense clumps that might one day birth new stars. In a way, these dark lanes are cosmic incubators, hiding the earliest stages of star formation from prying eyes, but the real mystery lies in their composition. Spectroscopic studies have detected organic molecules lurking within these dust lanes, complex carbon-based compounds that shouldn't survive the nebula's harsh radiation. Yet there they are, clinging to the dust like microscopic hitchhikers. Some scientists speculate these molecules could be the precursors to more complex life-building blocks, sheltered within the lane's protective shadows. It's as if the nebula is weaving a tapestry of cosmic ingredients, stitching together the very materials that might one day seed planets or even life itself. The dark lanes remind us that even in a nebula ablaze with light, darkness plays a vital role. Without these dusty filaments, the Orion Nebula's glowing gas would lack its dramatic contrast, its sense of depth, its haunting beauty. They're the universe's way of painting with shadows, proving that sometimes what we can't see shapes the cosmos just as profoundly as what we can. And as telescopes peer deeper into their inky depths, who knows what other secrets these cosmic curtains might yet reveal? The Orion Nebula doesn't just glow with chaotic beauty, it's threaded with invisible forces that sculpt its every curve and tendril. Beneath the swirls of gas and bursts of starlight, an intricate web of magnetic fields weaves through the nebula like cosmic puppet strings, guiding the motion of material with unseen hands. Until recently, astronomers assumed these fields were relatively simple, acting like gentle guides for the nebula's gas. But new observations have shattered that assumption, revealing a magnetic landscape so tangled and dynamic it's rewriting our understanding of how star-forming regions operate. Picture the nebula's magnetic fields as a colossal, invisible fingerprint lines of force spiraling, looping, and kinking in ways that defy prediction. Some regions show fields so tightly wound they resemble springs, compressing gas into dense knots where new stars can form. Elsewhere, the fields stretch like rubber bands snapped by the violence of stellar winds, their broken lines splaying outward in chaotic arcs. The most startling discovery, these fields aren't passive bystanders. They're active players in the nebula's drama, fighting against gravity, radiation, and even each other to shape the environment. One of the clearest examples lies in the nebula's famous pillars, those towering columns of gas immortalized by Hubble. For years, scientists thought these structures were shaped solely by stellar winds. But magnetic fields, it turns out, are the hidden architects. Observations from radio telescopes reveal field lines running along the pillars' lengths like reinforcing rods, propping them up against the trapezium star's relentless radiation. Without this magnetic scaffolding, these cosmic spires would have crumbled eons ago. Even more bizarre are the field's interactions with newborn stars. As young stars spin, they drag magnetic lines with them, twisting them into knots that occasionally snap, releasing bursts of energy. These magnetic explosions can fling jets of material outward at incredible speeds or trigger sudden flares bright enough to outshine the star itself. Some researchers suspect these reconnection events might explain why certain protostars flicker unpredictably, like the Great Orion Nebula Variable, their light dimming and brightening as magnetic turmoil rips through their surroundings. But the biggest surprise came when astronomers mapped the fields across the entire nebula. Instead of the orderly patterns they expected, they found a fractal mess, fields within fields, each layer interacting in ways that mimic the complexity of turbulent fluids. It's as if the universe took a paintbrush dipped in magnetism and swirled it through the nebula at random, leaving behind a masterpiece of chaos. What makes these magnetic forces so crucial isn't just their strangeness, it's their role as unseen conductors orchestrating the nebula's evolution. They channel gas flows, shield fragile molecules, and even influence the spin of newborn stars, subtly shaping the futures of entire planetary systems. And as we uncover more of their secrets, one thing becomes clear. To truly understand the Orion Nebula, we must learn to see not just its light, but the invisible forces pulling its strings. The Orion Nebula isn't just a symphony of light, it crackles with an invisible energy, a torrent of high-energy X-rays that defy everything we thought we knew about stellar nurseries. Imagine stepping into what looks like a serene, glowing cloud, only to find it secretly a particle accelerator, blasting out radiation fierce enough to strip electrons from atoms. This is the nebula's X-ray surprise, a phenomenon so unexpected it forced astronomers to rewrite the rules of how young stars behave. For decades, scientists assumed newborn stars were relatively calm, their X-ray emissions weak or confined to fleeting flares. But when the Chandra X-ray Observatory turned its gaze toward Orion, it revealed a reality far more violent. The nebula teems with X-rays, not just from a few stars, but from hundreds, even thousands of them, each one crackling with energetic outbursts. Some of these young stars produce X-ray flares so powerful they briefly outshine the entire nebula, releasing in seconds what our sun would take years to emit. It's as if the Orion Nebula is peppered with miniature supernovae, each one a stellar toddler throwing a cosmic fit. The source of this chaos lies in the star's turbulent youth. Unlike mature stars like our Sun, which generate X-rays in predictable, steady processes, these young stars are magnetic monsters. Their interiors churn with plasma, twisting magnetic fields into knots until they snap, like rubber bands stretched too far, releasing pent-up energy in explosive flares. One theory suggests these stars might be starquakes on a colossal scale, their surfaces fracturing under the strain of rapid rotation, launching shock waves that heat the surrounding gas to millions of degrees. The result, X-rays that could, in theory, sterilize any fledgling planets forming nearby. But the real shocker wasn't the flares themselves, it was where they came from. Some of the most intense X-rays don't even originate from fully formed stars. Instead, they erupt from protostars, objects still midway through collapse, shrouded in thick cocoons of gas. These X-ray babies shouldn't technically be capable of such violent emissions, yet there they are, defying textbook models. Even more puzzling are the X-rays coming from seemingly empty patches of nebula, areas where no stars are visible. One leading explanation, invisible stellar corpses, brown dwarfs, or even rogue planets might be generating their own high-energy radiation, hidden behind veils of dust. What makes this X-ray frenzy so crucial isn't just its spectacle, it's the consequences. These emissions act like cosmic blowtorches, heating the surrounding gas and altering the chemistry of the nebula. Molecules that would normally stay intact get ripped apart, only to recombine into new, more complex forms. Some researchers speculate this relentless radiation might even cook the raw ingredients for life, transforming simple compounds into the building blocks of amino acids. And for any budding planets in the area, the X-rays could be a double-edged sword, sterilizing their surfaces while simultaneously enriching their atmospheres with exotic, high-energy chemistry. The Orion Nebula's X-ray surprise forces us to rethink how wild the universe truly is. Even in the cradle of star birth, where we expected gentle processes, nature operates with a ferocity that borders on the apocalyptic. Every flicker of X-ray light is a reminder that the cosmos doesn't follow our rules, it writes its own. And as we decode these high-energy messages, we're not just learning about distant stars, we're glimpsing the violent, radiant chaos that might have once shaped our own solar system's destiny. In the Orion Nebula, where stars blaze with ferocious intensity, there's a glaring cosmic census problem the massive stars are missing. Statistically, this stellar nursery should be teeming with giants, stars dozens of times heavier than our Sun, their brilliance dominating the nebula's glow. Yet when astronomers tally them up, the numbers don't add up. It's as if the universe played a cruel magic trick, vanishing its own brightest performers mid-act. So where did they go? One theory suggests these massive stars might be self-destructing at an alarming rate. Unlike their smaller, steadier siblings, hypergiants live fast and die young, burning through their fuel so quickly they can explode as supernova within just a few million years, a blink in cosmic time. Some might have already met their fiery ends, their remnants hidden within the nebula's swirling dust. Others could be on the verge of collapse, their cores buckling under their own weight before we've even had a chance to study them properly. But there's another, even wilder possibility. These stars didn't die, they fled. Recent simulations reveal that the chaotic gravitational dance within dense star clusters can slingshot massive stars outward at incredible speeds, ejecting them into interstellar space like cosmic cannonballs. Imagine a stellar game of pinball where the heaviest players get hurled the farthest. A few might still linger on the nebula's fringes, drifting undetected in the darkness. Others could have escaped entirely, destined to roam the galaxy as lone wolves, their origins forever a mystery. The plot thickens when you consider how these massive stars shape their surroundings. Their radiation and stellar winds are so intense they can clear out entire neighborhoods of gas, disrupting star formation and even preventing new giants from emerging. It's a case of cosmic feedback. The very stars the nebula births might also be stifling future generations. Some researchers speculate we're catching Orion in a lull, a brief quiet period between waves of massive star formation. Yet the most tantalizing clue comes from the nebula's chemistry. Traces of rare isotopes, elements forged only in the hearts of massive stars, linger in the gas, hinting at a hidden population that once existed. It's like finding fingerprints at a crime scene but no suspect in sight. Whether these stars vanished in explosions or escaped into the void, their absence leaves behind a trail of cosmic breadcrumbs, and following them might rewrite our understanding of how stellar nurseries evolve. The missing massive stars of Orion aren't just a celestial head-scratcher, they're a reminder that even the most studied corners of space keep secrets. Every gap in our knowledge is a window into deeper questions, and the answers could reshape everything we think we know about the life and death of the universe's brightest giants. Amid the fiery reds and deep blues of the Orion Nebula, one color dominates the cosmic palette, an ethereal, almost otherworldly green. This isn't just a visual quirk, it's a chemical fingerprint, a glowing signature written in light by one of the universe's most abundant elements, oxygen. But this isn't the oxygen we breathe. Here, it's been stripped of electrons, ionized by the nebula's fierce ultraviolet radiation, and forced into a luminous dance that paints the cosmos in shades of emerald and jade. The secret behind this glow lies in a process called forbidden emission, a term so dramatic it sounds like something out of a cosmic myth. In reality, it's a quantum quirk. When ultraviolet light from the trapezium stars blasts oxygen atoms, it knocks away two of their electrons, leaving behind ionized oxygen, O-3, as astronomers label it. These ionized atoms crave stability, and as they recapture electrons, they release energy in the form of light. Normally, this happens in a split second, but in the nebula's thin vacuum, the atoms take much longer to relax, emitting that signature green glow at wavelengths of 5,007 angstroms. The result, a radiant haze that blankets entire swaths of the nebula, as if space itself has been dipped in luminescent paint. But why does the green glow vary so dramatically across the nebula? Near the trapezium stars, where radiation is strongest, the oxygen is fiercely ionized, producing an intense, almost electric green. Farther out, where the UV light weakens, the glow softens into subtler hues, blending with the reds of hydrogen and the blues of scattered starlight. It's a cosmic gradient, a living map of where energy flows and where it fades. Some regions even appear patchy, their green glow fragmented by dark lanes of dust or twisted by shockwaves from newborn stars. The most fascinating detail: this green light shouldn't technically be visible to us at all. On Earth, the same process is nearly impossible to replicate because our atmosphere's density causes ionized oxygen to release its energy in collisions long before it can emit that telltale glow. It's only in the near-perfect vacuum of space, where atoms are sparse and collisions rare, that this forbidden light gets a chance to shine. That makes the nebula's green glow not just beautiful, but a rare window into quantum physics playing out on an interstellar scale. Yet the story doesn't end there. Mixed into this emerald canvas are whispers of other elements: hydrogen's deep red, sulfur's faint crimson, even the delicate violet of helium. Together, they form a spectral symphony, each note revealing the nebula's composition, temperature, and turbulence. And hidden within that symphony are clues to the nebula's future. The green glow marks where ionizing radiation is most intense, zones where new stars are least likely to form, their potential snuffed out by the very energy that makes the nebula shine. So the next time you gaze at the Orion Nebula's green hues, remember, you're not just seeing color, you're seeing the aftermath of a cosmic battle, where light wrestles atoms into submission, where the invisible becomes visible, and where the universe writes its secrets in wavelengths only the patient and curious can decode. One of the Orion Nebula's most breathtaking tricks of light doesn't come from a star at all. It's a masterclass in cosmic illusion. Nestled within its glowing expanse, what appears to be a single star wreathed in flickering flames is actually a stellar mirage, a dazzling deception crafted by the nebula's own dust. This is the flaming star illusion, a spectacle where physics and perspective conspire to fool even the most seasoned observers. At the heart of this illusion lies a simple yet extraordinary process: light scattering. The nebula's dust particles, tiny flecks of carbon and silicate, act like celestial prisms, catching starlight and tossing it in every direction. But here's the twist: these particles don't scatter all colors equally. Blue light, with its shorter wavelengths, gets bounced around far more than red, creating an effect similar to Earth's sky appearing blue while sunsets glow crimson. In the nebula, this scattering paints certain stars in an eerie, fiery aura, as if they're burning within their own luminous halos. The star at the center of this illusion isn't actually a flame. Instead, it's backlit by the nebula's glow, its light filtering through dense curtains of dust that stretch across the foreground. This dust absorbs and re-emits the star's light, smearing its sharp point into a smoldering, diffuse radiance. From our vantage point, the result is uncanny: a starlit silhouette framed by what looks like swirling fire, as though the star is being consumed by its own brilliance. Infrared observations peel back the curtain on this cosmic sleight of hand. At these wavelengths, the dust becomes nearly transparent, revealing the true star behind the veil: ordinary, unremarkable, and utterly devoid of flames. The illusion only holds invisible light where our eyes and telescopes fall prey to the nebula's artistry. It's a reminder that in space, seeing isn't always believing. What makes this phenomenon so mesmerizing isn't just its beauty, it's the physics behind the curtain. The flaming star is a natural lab for studying how light interacts with interstellar dust, offering clues about the size, composition, and distribution of these microscopic grains. Some particles might be fluffy, fractal-like aggregates that scatter light in complex ways, while others could become packed and smooth, reflecting it more uniformly. Each flicker and hue in the illusion holds data, a hidden message about the nebula's hidden architecture. But perhaps the most poetic lesson here is about perspective. The same dust that obscures and distorts also creates grandeur, transforming simple starlight into something mythical. The universe isn't just a collection of facts, it's a stage for illusions, a place where reality and perception dance in ways that keep us forever curious. And in the Orion Nebula, that dance is performed with flames that don't burn and stars that only pretend to be on fire. There's a shadowy figure frozen mid-stride within the Orion Nebula, a cosmic sprinter eternally dashing through the glowing gas, the legendary Running Man silhouette. This isn't just another dark smudge against the nebula's brilliance. It's a celestial Rorschach test, a shape so uncannily human it ignites the imagination. Stretching nearly 2 light-years across, this formation of cold, dense dust appears like a stick figure in full sprint, legs outstretched, arms pumping, as if racing toward some unseen finish line in the void. What makes the Running Man so captivating isn't just its shape, it's the sheer improbability of its existence. Dark nebulae like this one are common, but rarely do they align so perfectly with our pattern-seeking brains to mimic something so distinctly familiar. The figure we see is actually a chance arrangement of interstellar soot, a twist of opaque material backlit by the nebula's glow. Yet the illusion is so convincing it feels intentional, as if the universe itself paused to sketch a stick figure into the cosmos. Scientifically, the Running Man is classified as Sharpless 279, a reflection nebula where dust doesn't just block light, it scatters it. The trapezium star's intense radiation hits these dust grains, bouncing off them like headlights in fog, giving the edges of the silhouette an eerie, bluish halo. This interplay of shadow and light creates depth, making the figure appear three-dimensional, as though it's truly leaping through space. But peer closer and the magic unravels. The head is a knot of gas, the torso a chance overlap of filaments, the limbs mere tendrils of debris stretching across the abyss. The Running Man isn't just a curiosity, it's a dynamic structure. Over millennia, stellar winds from nearby stars will erode its edges, slowly blurring the sprinting figure into oblivion. Already, the silhouette's outline flickers with tiny changes, pockets of dust heating up or dispersing under the relentless radiation. Some astronomers compare it to a sand sculpture on a windy beach, its shape fleeting, its existence temporary. But perhaps the most fascinating thing about this cosmic mirage is what it reveals about us. Humans are hardwired to see faces and figures in randomness, a phenomenon called pareidolia. It's why we spot animals in clouds or the man in the moon. The Running Man taps into that instinct, bridging the gap between cold astrophysics and warm creativity. It reminds us that the universe isn't just a collection of data, it's a canvas, and sometimes, against all odds, it paints something that feels strangely, wonderfully alive. So the next time you gaze at the Orion Nebula, spare a thought for its phantom sprinter. Though it's merely dust and chance, it stands as a testament to the beauty of perspective, where science and storytelling collide, and where even the darkest corners of space can spark the brightest flames of wonder. Tucked within the swirling brilliance of the Orion Nebula, a shadowy gash splits the cosmic canvas, a bizarre formation astronomers call the fish mouth. This isn't just another dark patch. It's a gaping void, an almost perfectly defined wedge of blackness that seems to bite into the nebula's glowing gas like a celestial predator taking its first savage bite. But look closer, and this apparent emptiness reveals itself as something far more extraordinary. A dense, bustling nursery where stars are being born in near-total darkness, shielded from the chaotic radiation beyond. The fish mouth gets its name from its uncanny resemblance to an open jaw, two dark, converging lanes of dust forming a V-shape, framed by the nebula's luminous lips of ionized gas. In telescopic images, the effect is startling, as if the cosmos has sculpted a colossal sea creature mid-snap, frozen forever in the act of devouring starlight. Yet this structure isn't static. The jaws are actually dynamic walls of cold molecular gas, so thick they absorb nearly all visible light, creating an inky silhouette against the nebula's glow. What makes this region so fascinating isn't just its shape, it's the secret activity hidden within. While the trapezium star's fierce ultraviolet radiation evaporates gas clouds elsewhere in the nebula, the fish mouth's dense interior remains eerily intact, a fortress against the storm. Here, gravity works undisturbed, quietly pulling together pockets of gas and dust into ever tighter knots. Infrared telescopes pierce the darkness to reveal a hive of protostars, dozens of stellar embryos, each one cocooned in its own swirling disk, slowly gathering mass. Some of these infant stars are so young they haven't yet ignited hydrogen fusion. They glow faintly with only the heat of their contraction, like embers smoldering in a cosmic furnace. But the fish-mouth's real magic lies in its paradox. Though it appears lifeless to the naked eye, it's one of the nebula's most fertile zones. Without the protective darkness of those dust lanes, the delicate process of star formation would be impossible here. The same radiation that paints the nebula's gorgeous colors would tear apart these fragile stellar nurseries before they could take shape. It's a delicate balance. The fish-mouth's darkness isn't emptiness, but a shield allowing nature to work undisturbed in the shadows. Some of the most massive stars in Orion might have begun their lives in such hidden pockets. As they grow, their own stellar winds will eventually blow away their dusty cribs, emerging like butterflies from a cosmic chrysalis. Until then, the fish-mouth keeps its secrets, a reminder that sometimes the universe's most creative work happens not in the light, but just beyond it, in the quiet dark where gravity weaves its slow, invisible spells. For thousands of years, humanity has gazed up at the constellation Orion and fixed their eyes upon one particular point of light, not a star, but a smudge of cosmic fog hanging from the hunter's celestial belt. The Orion Nebula's place in the sky isn't random. It sits at the heart of Orion's sword, a subtle line of stars that cultures across the globe have woven into myth, navigation, and even timekeeping. This positioning has transformed the nebula from a mere cloud of gas into a universal waypoint, a glowing landmark etched into humanity's collective memory long before telescopes revealed its true nature. To ancient civilizations, the sword's middle star, the nebula itself, was anything but ordinary. The Maya saw it as the smoke from a cosmic fire, while Aboriginal Australians recognized it as a group of young men dancing in the heavens. Norse legends imagined it as Freya's distaff, a tool for spinning the threads of fate. Even without knowing what it truly was, these cultures instinctively understood this patch of light held significance, its faint glow setting it apart from the pinpoint stars around it. The nebula's placement made it irresistible, not too bright to be blinding, not too dim to ignore, perfectly positioned to spark curiosity across generations. For navigators, the sword's alignment was a gift. Orion's position near the celestial equator meant it was visible from nearly every inhabited corner of Earth, rising and setting with predictable regularity. Polynesian voyagers used it to guide their canoes across the Pacific, while desert travelers relied on it to mark seasonal shifts. The nebula, glowing softly at the sword's center, became a natural bullseye, a reference point so reliable it functioned as a cosmic compass. Even today, amateur astronomers often start their stargazing sessions by locating the sword, using it as a stepping stone to explore deeper wonders. But the nebula's cultural impact goes beyond practicality. Its position in Orion, a constellation associated with hunters, warriors, and heroes, infused it with symbolic weight. In Renaissance Europe, astronomers like Christian Huygens turned their early telescopes toward the sword and gasped at the nebulous star they found, sparking centuries of scientific inquiry. For artists and poets, the nebula's hazy glow became a metaphor for mystery itself, a celestial ink blot onto which humanity projected its dreams of creation and infinity. What makes this alignment so remarkable is how accidental it truly is. The nebula just happens to sit along our line of sight within Orion's sword, a chance arrangement that grants us a front row seat to its stellar fireworks. From another star system, the constellation's shape might look completely different, the nebula invisible or relocated. Yet here we are, blessed with a vantage point where this cosmic cradle aligns with one of our most iconic celestial patterns. It's a reminder that sometimes the universe places its greatest wonders right where we can't help but notice them hanging like a jeweled pendant from the belt of a mythical hunter, waiting to be explored. Just beyond the Orion Nebula's radiant borders, another iconic cosmic silhouette looms in the darkness, the Horsehead Nebula. At first glance, these two celestial landmarks seem worlds apart. One a vibrant stellar nursery ablaze with color, the other a brooding, shadowy figure carved from cold interstellar dust. But peel back the layers and an astonishing possibility emerges: these nebulae might be cosmic siblings, shaped by the same ancient cataclysms and bound by a shared history of violence. The clue lies in their motion. Both nebulae drift through space at eerily similar velocities, their trajectories tracing back to a common point of origin. Astronomers studying their proper motion, the slow, steady path they carve across the galaxy, have noticed something peculiar. Rewind the clock a few million years, and the Orion and Horsehead nebulae appear to have been part of the same colossal gas cloud, a sprawling stellar factory stretching hundreds of light years. Then something catastrophic happened. The shock wave from a nearby supernova, or perhaps the gravitational kick of a passing star cluster, sent fractures rippling through the cloud, splintering it into fragments. One piece became the Orion Nebula, its gas compressed and ignited by newborn stars. The other, richer in stubborn dust, collapsed into the dense, sculpted forms we now recognize as the Horsehead. But the connections run deeper than mere motion. Spectroscopic analysis reveals nearly identical chemical fingerprints in both nebulae, the same ratios of hydrogen, carbon monoxide, and even complex organic molecules. It's as if scientists are comparing two pieces of shattered pottery, finding their edges fit perfectly together. Even more telling are the magnetic fields. Recent observations show the Horsehead's intricate field lines align in ways that mirror the Orion Nebula's own hidden magnetic architecture, suggesting they were once threaded by the same cosmic forces. The most compelling evidence, though, comes from the stars themselves. The Horsehead Nebula's backdrop is lit by Sigma Orionis, a young, massive star whose intense radiation etches the dark nebula's famous profile. Here's the twist: Sigma Orionis belongs to the same stellar association as the Trapezium Cluster, the very stars powering the Orion Nebula's glow. These stellar families share not just a neighborhood but a pedigree, born from the same ancestral gas cloud before being scattered like cosmic diaspora. What makes this theory so thrilling isn't just the past it reconstructs, it's the future it predicts. The same forces that forged these nebulae are still at work. The Horsehead's iconic shape, slowly eroding under stellar radiation, mirrors the fate of the Orion Nebula's own dark lanes. Given enough time, both will dissolve, their material recycled into new stars, new planets, perhaps even new life. They're snapshots of the same story, captured at different chapters, one ablaze with youth, the other fading into twilight. So the next time you spot the Horsehead's Inkai profile, remember, it's not just a bystander to Orion's brilliance. It's a surviving piece of the same cosmic masterpiece, a reminder that even in the vastness of space, nothing ever truly drifts alone. At the heart of the Orion Nebula's swirling chaos lies an enormous void, a cosmic hollow so vast it could swallow our entire solar system 1,000 times over. Astronomers call this structure the superbubble, a colossal cavity carved out by the relentless stellar winds of massive young stars. But here's the puzzle: this bubble shouldn't exist. Or at least it shouldn't still be here. The math is simple. With the kind of energy pouring into the nebula from stars like those in the Trapezium Cluster, the superbubble's delicate walls should have shattered eons ago, torn apart by the very forces that created them. Think of blowing up a balloon in a hurricane. That's the fragility we're dealing with. Yet against all odds, this bubble persists, its edges sharp, its structure eerily intact. It's as if the nebula itself is defying the laws of physics, holding its shape against unimaginable cosmic turbulence. The secret might lie in what we can't see. Some astronomers suspect hidden magnetic fields crisscross the bubble's interior, acting like cosmic rebar to reinforce its structure. Others point to the bubble's sheer scale. Its size alone might buy it time, the vast distances between shock waves allowing shocks to dissipate before they can fully disrupt it. Then there's the wildcard theory, past supernova. If one or more massive stars in the region have already exploded, their blast waves could have temporarily inflated the bubble to its current proportions, leaving behind a more resilient shell than pure stellar winds could create. But the superbubble isn't just a scientific curiosity, it's a time capsule. Embedded in its walls are clues about the nebula's most violent epochs, layers of compressed gas and dust that record ancient stellar outbursts like tree rings chronicling droughts. Some sections glow with unusual chemistry, hinting at elements forged in long-dead stars and blasted into the void. Other regions ripple with strange textures, as if the bubble's surface is frozen mid-shudder, caught in the act of resisting destruction. What makes this structure so fascinating isn't just its defiance of expectations, but what it reveals about stellar feedback, the way stars shape their own environments. The superbubble is nature's perfect paradox, a destructive force that creates order, a zone of emptiness that teems with scientific riches. Every time we think we've unraveled its mysteries, it offers up new questions, reminding us that even in the most studied corners of space, the universe still keeps a few secrets in reserve. Deep within the Orion Nebula's swirling gases, a discovery rippled through the scientific community that redefined our understanding of cosmic chemistry: traces of water. Not just a few scattered molecules, but enough to fill Earth's oceans thousands of times over, hidden in the nebula's icy dust grains and vaporized plumes. This wasn't just any water, it was the kind that could one day drizzle onto alien worlds, filling lakes, carving valleys, and perhaps even cradling life. The first clues came from radio telescopes tuned to specific frequencies, catching the faint song of water molecules vibrating in space. Each molecule acts like a microscopic tuning fork, emitting a unique radio signature when it flips its orientation. In the nebula's colder regions, water freezes into icy mantles coating dust grains, creating vast reservoirs of solid ice. Near young stars, though, ultraviolet radiation blasts these ices back into vapor, creating shimmering halos of steam that glow in infrared light. The sheer abundance stunned researchers. In some pockets, water outnumbers carbon monoxide, one of space's most common molecules. But how did this water get here? The answer lies in chemistry older than our solar system. On dust grains barely wider than a virus, oxygen atoms from dying stars bond with hydrogen floating between the stars. The process is slow, almost meditative. An atom here, a collision there, until, molecule by molecule, the building blocks of oceans accumulate. Some of these water molecules formed in the frigid depths of the molecular cloud that birthed the nebula, while others were cooked up in the shocks of stellar winds, their ingredients smashed together by violence. What makes this discovery so groundbreaking isn't just the water's presence, but where it's headed. Protoplanetary disks around young stars, the very cradles of future planets, are drenched in this cosmic moisture. When those planets form, the water gets baked into their crusts, vented into their atmospheres, or frozen into their comets. Some models suggest a single such disk might contain enough water to seed an entire planetary system with the stuff of life. And here's the kicker: the Orion Nebula's water isn't unique. If it's happening here, it's likely happening everywhere stars are born. Yet the real magic lies in the details. Spectroscopic studies reveal this water isn't pure H2O. It's laced with deuterium, a heavier form of hydrogen. The ratio of deuterium to normal hydrogen acts like a cosmic barcode tracing the water's history. In Orion, that ratio matches what we see in Earth's oceans and in comets, hinting that our planet's water might have originated in a nebula much like this one. It's a humbling thought. Every drop in your glass, every crashing wave might have once floated in a stellar nursery, waiting for gravity to weave it into a world. The Orion Nebula's water is more than a scientific curiosity, it's a promise. Where there's water, there's potential, not just for life as we know it, but for the very landscapes that make living worlds possible. And as we peer deeper into this cosmic oasis, we're not just studying distant chemistry, we're glimpsing the origins of our own blue planet and perhaps countless others like it. Among the countless stars in the Orion Nebula, some don't just shine, they waltz. These aren't solo performers but tightly bound pairs locked in gravitational embraces, swirling around one another in orbits so chaotic they've left astronomers scratching their heads. Normally, binary stars follow predictable paths, their movements cleanly explained by Newtonian physics. But here in the nebula's crowded stellar nursery, the rules seem to break down. Partners whip around each other at breakneck speeds, their trajectories wobbling unpredictably like drunk dancers stumbling across a ballroom floor. Take the system known as Theta 1 Orionis C, for example. This massive binary pirouettes at the nebula's heart, its two stars circling so close they could fit between our Sun and Mercury. Yet instead of tracing smooth ellipses, their paths kink and twist, as if some unseen hand keeps nudging them off course. The culprit, the nebula's dense environment. With so many stars packed into such a small space, each binary isn't just influenced by its partner's gravity. It's constantly jostled by passing neighbors, their tugs warping orbits into shapes textbooks never predicted. It's a celestial mosh pit where no dance stays the same for long. Even stranger are the systems where one star seems to lead while the other lags behind, their orbits desynchronized like partners missing each other's rhythm. In some cases, the smaller star loops wildly around its companion, its path resembling a spirograph drawing more than a stable ellipse. These lopsided dances suggest hidden forces at work. Perhaps one star harbors an undiscovered companion, its gravity warping the duo's movements from the shadows. Or maybe the stars themselves are asymmetrical, their uneven mass distribution sending their orbits off balance. The most baffling examples are the binaries that shouldn't exist at all. Conventional wisdom says stars this close, separated by less than the distance from Earth to the Sun, should have either merged or torn each other apart during their fiery births. Yet here they are, spinning in precarious harmony, as if the universe enjoys flaunting its exceptions. Some researchers think magnetic fields might be acting like cosmic bungee cords, stabilizing these reckless pairs just enough to keep them from catastrophe. Others speculate these stars formed differently, collapsing from a single twisted ribbon of gas that naturally braided them together. What makes these stellar dances more than just a cosmic curiosity is what they reveal about star formation itself. In calmer regions of space, binaries tend to follow orderly rules, but Orion's turbulence, its dense gas, its crowded stellar neighborhoods creates a laboratory of chaos, showing us how gravity behaves when pushed to extremes. Every erratic orbit, every wobbling path is a clue about the forces that shape not just these stars, but potentially every multiple star system in the galaxy. And perhaps the most humbling thought, these dances are temporary. Given enough time, gravitational interactions will either stabilize the wildest orbits or fling the stars apart entirely. What we're witnessing is a fleeting moment in a billion-year saga, a snapshot of celestial adolescence where the rules are still being written and every misstep teaches us something new. So the next time you gaze at Orion's shimmering clouds, remember, hidden in that glow are stars that don't just shine, but sway, spin, and stumble their chaotic waltz, a reminder that even gravity has its rebellious phases. The Orion Nebula's glowing gases aren't the only remnants of its violent past hidden in the infrared spectrum. Faint looping structures weave through space like celestial fingerprints, barely visible even to our most advanced telescopes. These ghostly loops emerge only when we peer through the dust-piercing eyes of infrared observatories, revealing delicate filaments that curl and twist across light years of space, their ethereal glow telling stories of explosions that rocked the nebula long before human eyes turned skyward. What makes these structures so extraordinary is their sheer scale. Some stretch farther than the distance between our Sun and its nearest stellar neighbors, yet remain so tenuous they'd vanish if viewed head-on. Unlike the nebula's sharp-edged pillars or defined bubbles, these loops appear almost translucent, their forms blurred as if painted with cosmic watercolors. Their infrared signature suggests they're composed of dust that's been gently heated not by the trapezium star's harsh ultraviolet radiation, but by some ancient, softer glow that's since faded into history. The leading theory points to stellar outbursts from the nebula's wild youth. Massive stars, now long dead, may have undergone violent convulsions, colossal eruptions, or final death throes that sent shockwaves rippling through the surrounding gas. Like throwing a stone into a pond, these waves would have pushed dust outward in expanding shells, which over millennia stretched and warped into the graceful arcs we see today. Some loops even appear to intersect, suggesting multiple cataclysms occurring at different epochs, their aftereffects preserved in this delicate infrared fossil record. Yet not all these loops may be ancient. Recent observations hint that some could be the footprints of ongoing, unseen activity. Perhaps protostars hidden so deeply in dust that their outbursts only betray themselves through these subtle, far-reaching ripples. One particularly intriguing loop aligns eerily with a known X-ray source, fueling speculation that a young star's explosive tantrum might still be reverberating through the nebula's depths, its energy imprinting these faint traces as it goes. The ghostly loops challenge our perception of time in stellar nurseries. While the Orion Nebula's visible structures change over human timescales, these infrared whispers operate on a different clock. Some may be hundreds of thousands of years old, lingering long after their creators vanished. Their cosmic echoes, fading but not yet gone, reminding us that the nebula's history is written not just in its brilliant present, but in these barely perceptible scars from a more turbulent past. And as infrared telescopes grow more sensitive, each new loop discovered adds another verse to the Orion Nebula's epic, a story far richer and more complex than its beautiful visible light portrait suggests. Nestled among the Orion Nebula's kaleidoscope of blues and greens, one region burns with an unusual crimson glow, a strange, geometric patch that astronomers call the nebula's red rectangle analog. At first glance, this ruddy anomaly seems out of place, its sharp angles and saturated hue more reminiscent of the famous red rectangle nebula in Monoceros than the chaotic swirls of Orion. But peer closer and the similarities become uncanny, not just in color, but in the bizarre chemistry that makes both structures shine with such otherworldly intensity. The secret lies in a process called red fluorescence, where certain carbon-rich molecules absorb invisible ultraviolet light and re-emit it as deep red. In both nebulae, the culprits are polycyclic aromatic hydrocarbons, PAHs, for short, complex organic compounds that act like cosmic dye. These molecules, often found in soot or diesel exhaust on Earth, thrive in the harsh environment of dying stars and stellar nurseries. When bathed in UV radiation, they don't just reflect light, they transform it, creating that signature ruby glow that defies typical nebula palettes. But the parallels run deeper than mere pigmentation. Both the red rectangle and its Orion counterpart exhibit eerie geometric symmetry, their shapes constrained by unseen forces. In the red rectangle, twin stars whip around each other in such a precise dance that they've sculpted their surrounding gas into near-perfect X-shapes. Orion's red region, while less perfectly angular, shows similar hints of order, its edges unnaturally straight for a nebula known for its fluid chaos. Some researchers suspect hidden binary stars or even powerful magnetic fields might be shepherding the gas into these unnatural formations, like invisible hands folding cosmic origami. The real jaw-dropper, though, is what these nebulae reveal about carbon's cosmic journey. The same PAHs that paint both regions red are among the most complex organic molecules found in space, precursors to the building blocks of life. Their presence in such distinct environments, one a dying star's ejector, the other a bustling stellar nursery, suggests carbon gets around, hitchhiking on dust grains or comets to seed the galaxy with its chemistry. It's as if the universe has a favorite color and it keeps painting with it wherever the conditions are right. Yet for all their similarities, Orion's red zone throws scientists a curveball. Unlike the red rectangle, which sits in relative isolation, this crimson patch is bathed in the trapezium star's relentless radiation conditions that should tear fragile PAHs apart. Their survival hints at some unseen shielding, perhaps dense knots of gas acting like cosmic bunkers. Or maybe the molecules are constantly reforming, their broken pieces reassembling faster than radiation can destroy them. Either way, this stubborn red splash challenges assumptions about where complex chemistry can thrive. What makes this cosmic color match so fascinating isn't just the science, it's the storytelling. Two wildly different nebulae, separated by thousands of light years, both whispering the same chemical secrets in shades of scarlet. One represents an ending, the other a beginning, yet both glow with the same organic signature. It's a reminder that across the vast canvas of space, certain patterns repeat not by chance, but because the laws of chemistry and physics paint with the same brushes, whether they're sketching a dying star's final masterpiece or a nursery's first rough strokes. In the frenzied stellar nursery of the Orion Nebula, some stars may have committed the ultimate cosmic crime, devouring their own siblings. Astronomers studying this region have uncovered disturbing clues suggesting that certain massive stars didn't just form peacefully, but grew to their colossal sizes through acts of stellar cannibalism, consuming smaller neighbors in a gravitational feeding frenzy. The evidence lies in the nebula's unruly dynamics. Young stars here aren't born in orderly isolation. They emerge in dense, crowded clusters where gravitational tugs of war are constant. Under these chaotic conditions, close encounters between stars can quickly turn deadly. Smaller stars straying too near a massive sibling might find themselves captured, their orbits decaying until they spiral inward, eventually torn apart and absorbed. The result, a star that bulks up unnaturally fast, packing on stellar mass not just through gas accretion but by literally digesting its kin. One prime suspect is Theta 1 Orionis C, the Trapezium Cluster's most massive star. Its extreme size and volatile behavior have long puzzled astronomers. How could a star so young already weigh in at over 40 solar masses? Traditional models of star formation struggle to explain its rapid growth, but the cannibalism theory offers a compelling alternative. If this star absorbed one or more smaller companions during its chaotic infancy, that could account for both its staggering mass and the erratic wobbles in its motion, as if it's still settling after a violent feast. The smoking gun might be chemical. Stars that consume others often bear telltale digestive traces, unusual abundances of heavy elements in their outer layers, the stellar equivalent of food residue. Recent spectroscopic studies of Orion's giants have detected strange chemical enrichments that don't match typical nebula compositions. Some elements appear concentrated in ways that suggest they weren't slowly accumulated but dumped all at once, like a cosmic stomach processing a sudden, hefty meal. Yet the most chilling evidence comes from the nebula's kinematics. High-resolution observations reveal rogue stars hurtling through space at bizarre angles, possible survivors of near-fatal encounters, flung away by the gravitational slingshot of a cannibalistic near-miss. Others show peculiar disk disruptions, their planet-forming rings bent or warped as if violently disturbed by a passing predator. These scars paint a picture of a nursery where survival isn't just about growing, it's about avoiding becoming someone else's lunch. What makes this phenomenon so unsettling isn't just the violence, it's the implications. If stellar cannibalism is common in Orion, it could rewrite our understanding of how the most massive stars form. Instead of growing steadily from vast gas clouds, some might leapfrog to enormity by absorbing rivals, shortcutting the slow process of accretion. That changes everything from how we model star clusters to how we predict their eventual fates. After all, a star that reaches supermassive status through cannibalism might live, die, and explode differently than one that grew peacefully. The Orion Nebula's suspected cannibals remind us that nature has no rules against cosmic predation, only consequences. In this glittering stellar cradle, beauty and brutality exist side by side, proving that even among newborn stars, it's not always survival of the fittest, but sometimes survival of the hungriest. Amid the Orion Nebula's luminous chaos, something invisible tugs at the fabric of space itself. Stars dart faster than they should, gas swirls against the pull of visible matter, and entire regions move as if haunted by unseen hands. These aren't ghosts, they're gravitational anomalies, cosmic discrepancies that have led some scientists to whisper a provocative possibility. Could dark matter, the universe's most elusive substance, be lurking within this stellar nursery? The evidence lies in motion. When astronomers map the nebula's dance, certain stars and gas clouds defy expectations, their velocities suggesting extra mass that telescopes can't detect. Normally, such behavior would be chalked up to hidden planets or failed stars. But here's the twist: even after accounting for every brown dwarf, rogue planet, and black hole candidate, the math still doesn't balance. The gravitational debt is too large, hinting at something far more exotic. Dark matter's fingerprints are subtle but telling. In one study, researchers traced the paths of stars near the nebula's eastern fringe, finding them orbiting an invisible center of gravity like moths around a darkened bulb. Simulations showed that a concentrated clump of dark matter, perhaps the size of a small star cluster but weighing hundreds of times more, could explain the anomaly. Elsewhere, filaments of gas curve unnaturally, their arcs bending as if snagged on hooks of unseen mass. Skeptics argue these effects could stem from ordinary astrophysical phenomena, magnetic fields, turbulence, or remnants of past supernova. But the most puzzling cases resist all conventional explanations. Take the Phoenix knot, a dense pocket of gas near the nebula's core that rotates with impossible cohesion, its outer layers whipping around as if anchored to an invisible spindle. No known stellar object could provide that kind of gravitational glue without being visible. If dark matter does hide here, it challenges everything we thought we knew about its behavior. Most models place it in galactic halos, not woven into star-forming regions like cosmic thread. Yet Orion's anomalies suggest it might clump differently in high-energy environments, perhaps interacting with the nebula's extreme radiation in ways we've never observed. Some theorists even speculate these could be dark matter streams, leftover tendrils from the nebula's formation, frozen in time like fossils of the universe's shadowy scaffolding. The implications ripple far beyond Orion. If dark matter congregates in stellar nurseries, it could alter how stars form, how planetary systems assemble, even how life's ingredients disperse. Its gravity might funnel gas into unexpected shapes, birth stars in hidden pockets, or shield fragile molecules from destructive radiation. Every unexplained wobble, every aberrant orbit, could be a clue to forces shaping the cosmos in ways we're only beginning to imagine. For now, the nebula keeps its secrets, but as instruments grow sharper, astronomers inch closer to unmasking these phantom masses, whether they're dark matter's first footprints in a starry cradle or something even stranger. One thing's certain: in a place where light reigns supreme, the darkest enigmas may hold the brightest revelations. The Orion Nebula's glow hides a secret written in wavelengths invisible to the naked eye, a mysterious set of spectral lines so unusual they've earned the dramatic title Forbidden Emissions. These aren't your typical neon sign colors from excited gas. They're the cosmic equivalent of a whispered scream, light produced under conditions so rare that scientists once believed they couldn't exist in nature at all. At the heart of this enigma are ionized atoms: oxygen, nitrogen, and sulfur stripped of electrons by the nebula's intense ultraviolet radiation. Normally, these ions would relax by emitting common, predictable wavelengths. But in the nebula's thin vacuum, where atoms are sparse and collisions rare, something extraordinary happens. Electrons transition between energy states that are usually forbidden by quantum mechanics, producing eerie, faint glows at specific wavelengths like 4,963 and 5,007 angstroms. It's as if the universe, for a fleeting moment, bends its own rules just to paint the nebula in these otherworldly hues. What makes these emissions so baffling is where they appear. Forbidden lines typically emerge in environments with densities 1,000,000 times lower than Earth's atmosphere, conditions thought impossible in a bustling stellar nursery like Orion. Yet here they are, flickering persistently across the nebula's expanse. The key lies in the delicate balance between radiation and emptiness. The trapezium stars flood the region with enough UV light to ionize atoms, while the vast distances between particles prevent the collisions that would normally suppress these quantum-defying transitions. It's a Goldilocks zone for rare physics, where chaos and isolation collide to create something beautiful. The real surprise came when astronomers discovered these forbidden lines aren't uniform. Some regions blaze with forbidden oxygen's greenish glow, while others shimmer with sulfur's deep red or nitrogen's subtle violet. This patchwork reveals hidden structures in the nebula, invisible density waves, magnetic field boundaries, and even the footprints of ancient stellar winds etched into the gas. Like cosmic litmus paper, the forbidden emissions map the nebula's invisible architecture, exposing currents and eddies that would otherwise stay hidden. Perhaps most astonishing is how these spectral oddities connect to the bigger picture. The same forbidden lines detected in Orion have been spotted in galaxies billions of light years away, offering clues about the early universe's chemical makeup. They're even helping astronomers identify the faintest, most diffuse gas clouds floating between galaxies, clouds so tenuous they'd be invisible without these quantum rule breakers lighting them up. So the next time you see an image of the Orion Nebula's vibrant colors, remember, the most fascinating light might be what you can't see. These forbidden emissions are more than just celestial curiosities. They're a reminder that even in the most studied corners of space, the universe still knows how to surprise us, bending its own laws just to send us a message written in wavelengths once thought impossible. Deep in the chaotic core of the Orion Nebula, supercomputer simulations have revealed a reality far stranger than astronomers ever predicted. A whirling vortex of gas and energy that physics says should have torn itself apart eons ago. This turbulent heart doesn't just pulse with activity. It defies the very laws that should govern it, spinning faster, lasting longer, and resisting collapse with a stubbornness that's rewriting our understanding of stellar nurseries. The simulations began as an attempt to solve a simple mystery. Why does the nebula's central region, packed with enough raw energy to evaporate entire star systems, remain so tightly bound together? When physicists fed the data into their models factoring in radiation pressure, magnetic fields, and the gravitational tug of war between stars, the results were astonishing. Instead of showing a stable equilibrium or gradual disintegration, the digital nebula developed a frenzied, self-sustaining whirlpool at its core. Gas didn't just flow, it twisted into fractal-like spirals, folding back on itself in patterns reminiscent of Van Gogh's Starry Night, but on a scale so vast it could swallow our solar system whole. What makes this turbulence so baffling is its resilience. Traditional astrophysics suggests such violent motion should dissipate quickly, like a spoon-stirred cup of coffee settling back to stillness. Yet Orion's heart keeps churning, its energy somehow replenished faster than it can bleed away. The key might lie in an unseen feedback loop. Stellar winds from the trapezium stars slam into surrounding gas, creating shock waves that reflect inward like echoes in a cosmic canyon. These rebounding waves inject fresh turbulence into the system, preventing it from ever quieting down. Simulated tracer particles reveal gas parcels following bizarre, loopy trajectories, as if caught in an endless celestial pinball machine. Even more startling are the magnetic fields. Threaded through the chaos like invisible puppet strings, they don't just guide the turbulence, they amplify it. The simulations show field lines getting stretched and twisted into braids by the nebula's rotation, storing energy like wound-up rubber bands. When these lines finally snap, a process called magnetic reconnection, they release violent bursts that heat the gas to millions of degrees, further fueling the maelstrom. It's a self-perpetuating engine where chaos begets more chaos in a cycle that challenges our assumptions about how energy dissipates in space. The real-world implications are profound. If such persistent turbulence is common in stellar nurseries, it could explain why some regions form stars far faster than theories predict. The constant churning would keep gas densities uneven, creating dense pockets where gravity can suddenly take over. It might also solve the mystery of why massive stars, which should theoretically blow away their own building materials, manage to grow so large. The simulations hint that the turbulence acts like a cosmic blender, continually recycling material back into the star-forming zones faster than radiation can clear it away. Yet for all their revelations, these digital experiments raise new questions. Some simulations produce structures eerily similar to the nebula's observed pillars and loops, suggesting turbulence sculpts its famous landscapes. Others show rogue vortices breaking off like celestial tornadoes, spinning independently for thousands of years. Entities that, if real, could harbor hidden protostars or rogue planets. The most unsettling outlier runs, those where the entire core suddenly detonates, its pent-up energy releasing in a single, catastrophic burst that reshapes the entire nebula in an astronomical blink. As supercomputers grow more powerful, each simulation peels back another layer of Orion's defiance. What emerges isn't just a portrait of a nebula, but a radical rethinking of how chaos and order dance in the cosmos. The turbulent heart doesn't just endure, it thrives on its own violence, a reminder that even in the cold vacuum of space, there are places where stability isn't the rule, but the exception. And as we decode its secrets, we're not just learning about Orion, we're glimpsing the untamed physics that might shape every stellar nursery in the universe. Most of us picture nebulae as timeless celestial paintings, unchanging masterpieces frozen in the depths of space. But the Orion Nebula has been caught red-handed, morphing before our eyes in ways that shattered astronomers' assumptions. Time-lapse observations spanning decades reveal a cosmic ballet of motion. Jets that flicker like sputtering fireworks, dust lanes slithering like living ink blots, and shock waves racing outward at speeds that would cross the gap between Earth and the Moon in mere hours. This isn't some distant galaxy where changes unfold over eons. It's dynamic, volatile, and rewriting our understanding of stellar nurseries in real time. Take the case of HH34, a Herbig-Haro object first photographed in the 1990s. What began as a slender, near-perfect jet of plasma has since fragmented into a series of glowing knots like beads on a necklace coming undone. Each knot marks a violent ejection from a hidden young star, with newer outbursts plowing into older material and creating luminous shock fronts. The entire structure has stretched visibly in just 20 years, an astronomical blink where we expected millennia of stillness. Even more astonishing are the changes in the fish-mouth dark lane, its edges fraying under radiation pressure like paper held to a flame. Infrared comparisons show entire sections of dust evaporating, their molecules torn apart atom by atom in a cosmic disappearing act. The real shock came when researchers stacked Hubble images side by side, revealing protoplanetary disks. those fledgling planetary systems warping and tilting over shockingly brief spans. One disk, originally face-on to our line of sight, now shows a pronounced tilt, its silhouette darkening as its angle shifts. The culprit, likely a close gravitational encounter with another star, proving these crowded stellar nurseries are anything but orderly. Meanwhile, near the Trapezium Cluster, looping filaments of gas have surged outward, their advance captured in snapshots separated by mere years. These aren't the sluggish drifts of typical nebula motion. They're supersonic tsunamis, their energy betraying violent stellar outbursts we somehow missed in real time. What makes these changes so revolutionary is how they force us to rethink timescales. Textbooks once described nebulae as slowly evolving, with alterations measurable only over centuries. Orion laughs at those notions. Here, stars can reshape their surroundings within a human lifetime, their tantrums etching visible scars across the gas. Even the nebula's famous pillars, those iconic towers immortalized by Hubble, aren't immutable. Simulations based on time-lapse data suggest some may completely dissolve within the next 50,000 years, a heartbeat in cosmic terms. The most humbling lesson: we're not just observing Orion's past, we're witnessing its present, a living theater where the next act unfolds faster than we ever dreamed. Every new image is a frame in a cosmic film still playing, and each revelation proves the universe doesn't wait for us to catch up. It dances on whether we're watching or not. In the age of viral headlines and clickbait astronomy, few claims about the Orion Nebula sparked as much frenzy as the so-called alien megastructure spotted in its depths. The story erupted when amateur astronomers analyzing old Hubble images pointed to peculiar light curves, strange geometric dimming patterns that, at first glance, didn't match known natural phenomena. Internet speculation exploded. Could these be signatures of Dyson spheres or other colossal cosmic engineering? The truth, as always, turned out to be far more fascinating than fiction, and a masterclass in why scientific scrutiny matters. The irregularities in question centered around a young star named V38 Orionis, where light fluctuations appeared unusually sharp and symmetrical, almost as if something large and artificial were passing in front. But when professional astronomers trained their instruments on the star, they found no evidence of alien handiwork. Instead, the culprit was a combination of two entirely natural factors: a warped protoplanetary disk and a cosmic illusion. V38 Orionis hosts a massive, tilted ring of gas and dust, one so thick it occasionally eclipses the star from our vantage point. As the disk rotates, its uneven edges create those perplexing light dips, like holding a crumpled piece of paper between a light bulb and your eyes, watching shadows shift in unpredictable ways. What made this case so instructive was how it highlighted the gap between perception and reality. The human brain is wired to seek patterns, especially ones that resemble familiar structures, a tendency that leads us to see faces in clouds or pyramids on Mars. In space, where data is often sparse and ambiguous, this instinct can run wild, but science operates differently. Researchers tested the alien megastructure hypothesis by looking for secondary evidence: heat signatures from hypothetical megastructures, gravitational effects on nearby objects, or chemical traces in the star's light. None materialized. Instead, infrared observations revealed the disk's telltale thermal glow, while spectroscopic data showed it was rich in silicates and ice, exactly what you'd expect from a young star's planetary construction zone. The Orion Nebula's alien megastructure hoax wasn't just a lesson in skepticism, it was a celebration of how science self-corrects. While viral stories thrive on mystery, real astronomy thrives on evidence. Every extraordinary claim became a stepping stone for deeper investigation, pushing telescopes and theories to their limits. And in the end, the truth proved just as wondrous as any sci-fi scenario: a baby star system caught in the act of forging planets, its chaotic disk bending light into shapes that, for a fleeting moment, made us question everything we knew. The universe doesn't need aliens to be astonishing. It just needs us to keep looking, testing, and staying curious. Deep within the Orion Nebula's churning clouds, an otherworldly chorus hums, a symphony of ultra-low-frequency vibrations rippling through the plasma at frequencies far below what human ears could ever detect. These aren't sound waves as we know them, but something far stranger, oscillations of charged particles, their rhythmic dances converted into eerie songs by radio telescopes. The process begins with the nebula's sea of ionized gas, where atoms stripped of their electrons jostle in the turbulent stellar winds. As these particles collide, they create pressure waves that propagate outward, not through air, but through the magnetized plasma itself, a medium where magnetic fields act like cosmic strings plucked by the motions of stars and shock fronts. What makes these plasma waves so mesmerizing is how they betray forces invisible to optical telescopes. When scientists translate the radio data into audible frequencies, the nebula reveals hidden textures, long, droning notes that hint at vast magnetic loops vibrating like cello strings, punctuated by sharp staccato bursts from stellar flares. Some sequences repeat at regular intervals, likely tied to the rotation of young stars whose magnetic fields whip the surrounding plasma into rhythmic pulses. Others resemble chaotic static, the aftermath of violent events like protostellar jets slamming into gas clouds at supersonic speeds. Together, they form a soundscape as dynamic as the nebula's visual fireworks, offering an entirely new way to listen to star formation. The most startling discovery came when researchers compared wave patterns across different regions. Near the trapezium stars, the plasma sings in higher frequency tones, reflecting the intense radiation that keeps gas fiercely ionized. Move toward the nebula's outer filaments, and the pitch drops into deeper registers, as if the universe itself were tuning a cosmic bass line. These variations aren't just artistic curiosities, they're precise diagnostics revealing temperature gradients, magnetic field strengths, and even the density of otherwise invisible dust lanes. A single sustained note might trace the path of a shockwave from a millennia-old supernova, while a sudden crescendo could mark the birth of a new protostar. Yet the true magic lies in how these waves interact. Simulations show they don't merely pass through one another, they collide, refract, and even cancel out in zones of destructive interference, creating pockets of eerie silence amid the cosmic noise. Some waves appear to spiral along magnetic field lines, corkscrewing through space like phonograph grooves playing a record written in plasma. Others get trapped in resonant cavities between dense gas clouds, bouncing back and forth until their energy dissipates. It's a reminder that even in the vacuum of space, vibrations carry stories, if only we have the right tools to hear them. This singing nebula challenges our very definition of sound. Without an atmosphere to propagate pressure waves, these oscillations exist in a realm between particle physics and acoustics, a reminder that the universe communicates in frequencies beyond our narrow sensory range. And as radio telescopes grow more sensitive, each new decibel of this cosmic chorus brings fresh revelations, turning what was once silent majesty into a symphony of secrets waiting to be decoded. The Orion Nebula won't blaze forever. Already, subtle changes ripple through its clouds, signaling the beginning of an inevitable transformation. Within the next 100,000 years, the nebula's dazzling stellar nursery will start shutting down, its gas evaporating like morning mist under the trapezium star's relentless ultraviolet assault. The first signs are visible now, the delicate tips of the iconic pillars slowly dissolving, their edges fraying as radiation strips away molecules atom by atom. This isn't just erosion, it's the unraveling of an entire cosmic ecosystem, a countdown to when the nebula's glow will fade from brilliant emerald to a faint, diffuse haze. Projections paint a stark timeline. In roughly 2 million years, a blink in cosmic terms, the nebulous star-forming heyday will end. The remaining gas reserves, now too thin and hot to collapse into new stars, will be blown outward by stellar winds, creating a vast, ghostly shell around the emerging Orion OB1 association. This loose cluster of young stars, the nebula's surviving offspring, will inherit the region, their gravity no longer strong enough to hold the dissipating gas. The trapezium stars themselves face violent demises. Some will explode as supernova, their shockwaves injecting one last burst of energy into the fleeing gas, while others may collapse into black holes, leaving behind only gravitational echoes of their former brilliance. The dispersal won't be uniform. Dense knots like the fish mouth and dark lanes may linger longer, their compact structures resisting evaporation. These final holdouts will become isolated islands in an increasingly empty void, their shadows stretching across light years before finally succumbing. Infrared telescopes will witness the nebula's death throes in reverse. What's now a bright optical spectacle will transition into an infrared-dominated realm, where only warm dust and the faint heat of failed stars remain visible. Eventually, even these embers will cool, leaving behind a field of mature stars drifting apart, their shared nursery now just a memory written in their similar ages and trajectories. Yet the nebula's legacy won't truly vanish. The heavy elements forged in its star's oxygen, carbon, silicon, will mix with the interstellar medium, becoming raw materials for future nebulae. Some of this enriched gas might already be flowing into nearby star-forming regions like the Lambda Orionis ring, seeding new generations of stars with Orion's ashes. Planets forming in those distant eras could incorporate molecules that once swirled in the Orion Nebula's globe, perhaps even the same organic compounds that huddled in its dark molecular clouds. The most poetic fate belongs to the nebula's runaway stars, dozens of high-velocity escapees flung outward by gravitational slingshots are already carrying pieces of Orion across the galaxy. These stellar vagabonds, some with protoplanetary disks still intact, may one waywardly drift into other nebulae, their chemistry subtly altering new stellar nurseries. In this way, Orion's story won't end with its dispersal, but with its scattering, a cosmic diaspora of elements, momentum, and perhaps even the ingredients for life, cast adrift to shape whatever comes next. Long after the last wisp of gas has blown away, the Orion Nebula's true impact will linger in the stars it birthed, the planets they warmed, and the elements they forged. What we see today as a radiant tapestry is just one brilliant chapter in a saga stretching billions of years, a fleeting firework in the darkness, its sparks destined to ignite new wonders far beyond our sight. From vanishing stars to cosmic cannibalism, magnetic mysteries to phantom masses, the Orion Nebula isn't just a stellar nursery, it's a laboratory where the universe tests its wildest experiments. These 30 phenomena defy expectations at every turn. Pillars of gas that shouldn't stand, newborn stars flickering like faulty light bulbs, organic molecules surviving radiation that should tear them apart, and plasma waves humming tunes no human ear could hear. Each discovery peels back another layer of cosmic chaos, revealing how much we still don't understand about even our celestial backyard. Take the Trapezium Cluster's ruthless radiation, sculpting protoplanetary disks into comet-like tails while somehow nurturing resilient worlds. Or the ghostly loop's infrared echoes of ancient explosions hidden like cosmic graffiti beneath the nebula's vibrant glow. There's the fish-mouth star-forming shadows, the Running Man's pareidolia masterpiece, and the bizarre red rectangle patch where chemistry defies physics in shades of crimson. And let's not forget the nebula's greatest magic trick, water, oceans worth of it, forged on dust grains and destined for alien worlds, whispering that our own planet's seas might have started in a place just like this. What makes these mysteries so thrilling isn't just their strangeness, it's how they force science to adapt. Magnetic fields stronger than models predict, turbulence that refuses to fade, stars growing too big too fast, Each anomaly cracks open new questions about how the cosmos really works. Orion doesn't just follow the rules, it rewrites them, proving that even in well-trodden patches of space, wonder lurks in every wavelength. Now it's your turn. Which of these phenomena hooked your imagination? Was it the phantom sprint of the running man, the violent ballet of binary stars, or the eerie forbidden light defying quantum expectations? Drop your pick in the comments. We're obsessed with these cosmic riddles, and we'd love to hear which ones spark your curiosity. And if you're hungry for more deep dives into space's greatest mysteries, hit subscribe. The universe has countless stories left to tell, and we're just getting started.